This module will cover reciprocating engines. An airplane has an engine, which is commonly referred to as a propulsion system or a power plant. The reason is simply the engine not only powers the airplane to move through the air, but it also has other components attached to it in order to create electricity, vacuum suction, heat, etc. While most airlines and corporate airplanes use turbine-powered engines, general aviation aircraft typically use reciprocating engines. Most principal items in aircraft performance involve steady state or quasi-steady flight of the airplane. And we know in equilibrium that thrust equals drag and lift equals weight. In turbojets, thrust is produced directly from the engine. In propeller aircraft, the engine does not produce thrust directly. The engine produces power, which turns a propeller, and it's the propeller that develops an aerodynamic force, which is the thrust. Let's go over some of the basic definitions and units. Thrust is a force with units of pounds. Work is force times distance with units of foot-pounds. Power is work over time, which is force times distance divided by time, with units of foot-pounds per second. But we also know that distance over time is velocity in feet per second. So power is really just force times velocity. Or, in the case of aircraft, power is thrust times velocity. Since reciprocating engines involve rotating shafts, we can relate power to the rotational properties of torque and angular speed. Torque is force times the radius. Solving for force, we get force equals torque divided by the radius. Distance traveled at a point on the radius is the radius times the angular speed times the incremental time. If we substitute these relationships into the power equation, we get the equation in the yellow box. Basically, power equals torque times RPM with some scaling for units. The power of a reciprocating engine is often given in horsepower. So what exactly is 1 horsepower? Well, it was agreed that 1 horse can pull 100 pounds a distance of 330 feet in 1 minute. In foot-pounds per second, 1 horsepower is 550. After some manipulation of units, we get the equations in the yellow boxes. The first one covers linear power, and the second one covers rotational power. And both are in units of horsepower. Reciprocating engines have several cylinders. Inside of those cylinders, fuel and air are mixed, compressed, and then ignited. As this fuel-air mixture is ignited, its explosive force moves the piston inward. These pistons are connected to a crankshaft. And when the pistons move in and out, that causes the crankshaft to rotate. The propeller is connected to the crankshaft. So, as the crankshaft rotates, so does the propeller. You'll see other subsystems on the diagram like the induction system, pumps, and magnetos. Later, we'll walk through these systems in detail, as well as cover the 4-stroke cycle. Unfortunately, there's not just one type of horsepower. Students often get confused when working with the different types of horsepower, so we'll define each one now. The first is brake horsepower. It was named after an early device used to measure horsepower called a prony brake. It's measured with a dynamometer at the crankshaft. The next one is shaft horsepower. This will be less than brake horsepower because of gearing losses in reducing engine RPM to propeller RPM, and it's measured at the propeller shaft. The third one is thrust horsepower. This is the usable horsepower. It's less than shaft horsepower because of propeller efficiency loss. And do not confuse thrust horsepower with thrust. It's still a type of horsepower. Finally, we have propeller efficiency, which is the ratio of power output to power input, which is thrust horsepower divided by shaft horsepower. Now we'll examine what creates the thrust for the airplane to fly. As the combustion occurs in the cylinders, the pistons rotate the crankshaft, which directly drives the propeller. The propeller is actually twisted. This is simply to create equal thrust across the propeller blade. Since the propeller rotates at about its hub or center, the further the propeller extends out from the hub, the faster the tangential velocity. To create equal force throughout, the manufacturers twist the blade. Propellers are classified into 4 groups. The first is fixed pitch. This means the blades are fixed at one pitch angle. Maximum efficiency occurs at only one airspeed and one rotation. They're optimized for either climb or cruise or some intermediate value. The second is adjustable pitch. This means pitch setting can be adjusted on the ground with the engine stopped or the propeller removed. Once set though, the maximum efficiency occurs still at only one airspeed and one rotation. Third is controllable pitch. This means pitch can be controlled in the air by the pilot, usually restricted to either a takeoff setting, low pitch, or a cruise setting, high pitch. And the fourth one is constant speed. This means pitch is hydraulically or electrically controlled. Pilots select desired RPM with a lever, and a control governor adjusts the blade angle to maintain the RPM. For controllable pitch or constant speed propellers, the table shown gives representative blade angles used with respect to aircraft type. You can see how low pitch values are all in the 10 to 15 degree range, and high pitch values range from the 20s to the 50s. Propeller aircraft are limited on their top speed due to 1. Compressibility effects of the blade tip. 2. Forward speed impact on the blade's effective angle of attack. You can see in the diagram how the forward speed vector sums with the rotational velocity vector, resulting in a lower effective angle of attack seen by the blade. The basic principles of propulsion apply in that thrust is produced by providing the airstream a momentum change. The propeller achieves high efficiency by processing a relatively large mass flow of air, or mdot, and imparting a relatively small velocity change, v2 minus v1. Using momentum theory, we can analyze rotating propellers by assuming they are actuating disks, basically with infinite blades, and calculate an ideal propeller thrust. The final velocity of the propeller slipstream, v2, is achieved some distance behind the propeller. Because of the nature of the flow pattern produced by the propeller, 1/2 of the total velocity change is produced as the flow reaches the propeller disc. The mass of air passing through the propeller disc per unit time is mdot is rho a1 times the free stream velocity plus the incremental velocity delta v. The thrust generated is mdot multiplied by the total velocity change through the control volume. The result of summing all the forces on the control volume is shown by the equation in the yellow box. Here's a diagram showing the flow in motion. The power input to the ideal propeller is given by the equation P input is the thrust times the free stream velocity plus the incremental velocity delta V. The power output by the ideal propeller is P output is the thrust times the free stream velocity V infinity. The ideal propeller efficiency is then the output power divided by the input power. And there's the equation which results in V infinity divided by V infinity plus delta V. The ideal propeller efficiency can be manipulated to match the equation used for turbojets. The end result is 2 divided by 1 plus the ratio of V2 over V infinity. The highest efficiency is developed by producing thrust with the highest possible mass flow and the smallest necessary velocity change. This ideal model of propeller performance had many simplifying assumptions: infinite blades, inviscid flow, no propeller drag, etc. There are more sophisticated models that exist that use blade element theory or vortex theory. Another term you'll hear is advance ratio. The difference between the blade angle, which we will denote beta, and the effective angle of attack can be referred to as the effective pitch angle. It is a function of some proportion of the flight velocity and the velocity due to rotation at the wingtip. In terms of rotations per second, which we will denote n, the velocity due to rotation at the tip is b tangential equals 2 pi times n times the radius. In terms of the propeller diameter, we get b tangential is pi times n times the diameter d. The advance ratio, which we denote J, is defined as follows: V infinity over n times d. The advance ratio J is used to evaluate propellers, just like alpha is used for wing airfoils. While blade angle beta varies throughout the length of the blade, a representative value is measured at 75% of the blade length from the hub. This figure shows the variation of propeller efficiency with advance ratio for various values of blade angle. For each beta, the value of propeller efficiency increases with J until a peak is reached and then decreases. From this figure, one can see that a fixed pitch propeller may be selected to provide suitable performance in a very narrow range of J. Outside of this range, efficiency would suffer considerably. To provide good efficiency for a wider range of operation, the blade angle must be controllable. In the event of power plant malfunction, the blade angle should be set to 90 degrees. This is known as feathering the prop. This will stop the propeller from windmilling, which actually increases drag substantially. And you can see that in the graph below. On landing roll, using a flat pitch or reverse pitch will actually help slow the airplane down. Now that we've examined propellers, we need to select an engine that can provide the necessary power to rotate the propeller at the design RPM. Some types of reciprocating engines we'll look at are horizontally opposed, radial, inline, V-type, and X-type. And each type can use different methods of aspiration, fuel-air mixing, ignition, and cooling. Horizontally opposed engines are most common in light aircraft. The Piper Cherokee 6 uses a horizontally opposed engine, the Lycoming 0540. They are mainly air-cooled and they run smoothly. Aircraft from the early days used radial engines. The radial configuration enhances air cooling, but the large frontal area increases drag. Also, you need an odd number of cylinders to run smoothly. Inline engines have also been used, both upright and inverted. They typically have low frontal area, usually 4 to 6 cylinders. They're mainly liquid cooled, but they have a heavy crankcase, and they're tough to get running smoothly. For upright inline engines, ground clearance issues are something to consider, and for inverted, oil leak issues are something to consider. V and X-type engines have also been used. Here's some classics from Rolls-Royce. There are two methods of aspiration: normally aspirated like the Piper Cherokee 6, and turbocharging like the Piper Navajo. The turbocharger is a turbine-driven forced induction device that increases an internal combustion engine's efficiency and power output by forcing extra compressed air into the combustion chamber. This improvement over a normally aspirated engine's power output is due to the fact that the compressor can force more air and proportionally more fuel into the combustion chamber than atmosphere alone. The job of the carburetor is to mix fuel with air that gets sent to the cylinder combustion chambers. Fuel arrives at the carburetor and sits in the float chamber waiting to be used. To the side of the float chamber is the venturi, which is where the air passes through. As the air passes through the venturi, its velocity increases, which causes the pressure to decrease. Towards the bottom of the venturi, we find a fuel discharge nozzle, which is located near the area of low pressure. This draws the fuel out from the float chamber through the nozzle and mixes it with the air. Just past the venturi is the throttle valve. This controls how much of the fuel-air mixture is being sent to the cylinders. Fuel injection systems have many benefits over carbureted engines. Fuel injection engines reduce the amount of fuel required, increase engine power output, and allow for the precise use of the fuel. Rather than have a carburetor, a fuel-injected system is split up into different components. These consist of fuel pumps, a fuel control unit, a fuel manifold valve, and finally, fuel discharge nozzles. The fuel pump pumps fuel from the fuel tanks into the fuel control unit. Then, the fuel control unit regulates the specific amount of fuel needed based on the mixture and throttle settings. The fuel then gets sent to the fuel manifold valve, where it is dispersed and heads to the nozzles of each cylinder. This time the fuel does not mix with the air until immediately before entering the combustion chamber. Now that we discussed how we get fuel and air into the cylinders, let's talk about how we get that mixture to ignite. The ignition system is what provides the spark to the mixture. The major components of the ignition system include the magnetos, spark plugs, wires, and the ignition switch. A magneto consists of a rotating magnet that generates sparks of electricity. The spark that is generated is independent of the airplane's electrical system. That means if the airplane's electrical system were to fail, the magnetos would still be able to generate sparks for the engine to run. The energy generated from the magnetos is sent to the spark plugs. Spark plugs then release that energy, which ignites the fuel-air mixture, creating power to turn the propeller. Most airplanes have 2 magnetos, multiple sets of wires, and 2 spark plugs per cylinder in order to increase efficiency and reliability of the system. If one magneto fails or one spark plug fails, the engine will still run. However, power output will be slightly reduced as the engine is operating less efficiently. The last component of the is the ignition switch, which is the pilot's way of controlling the magnetos. In most general aviation aircraft, this switch is labeled off, right, left, both, and start. If the switch was to be placed off, then the magnetos would not be able to power the spark plugs. Therefore, the engine would not be able to run and it would turn off. If the switch was placed on the right or left position, then only that respected magneto would be powering its spark plugs. If the switch was positioned on the both selector, which is its normal position for flight, then both magnetos would be powering the spark plugs. Finally, the start position. This engages the starter, which turns the crankshaft to start the engine. In the cylinders, the spark plugs ignite the fuel-air mixture, moving the piston in the power stroke. There are also electronic ignition systems out there. There are two major ways to cool engines: air along with oil, and liquid cooling, which uses coolant much like a car. For air-cooled engines, oil passes through an oil cooler and proceeds to not only lubricate but also cool the engine. As the cool oil touches the hot engine, there's a heat exchange, meaning the oil becomes warmer but the engine becomes cooler. Then the oil returns back to the oil filter and oil cooler, and the process starts over. However, we also use air to cool the engine. The airplane flies through the air outside. Air flows through the inlet usually found in the front of the airplane. The outside air is colder than the engine. As the air flows over the engine, it cools it in the same manner that oil cools the engine. This method of cooling can be severely restricted, however, when the airplane is running at high RPM and at very low speed, such as when climbing. Airflow is minimized, causing higher temperatures. Some of the pros and cons of air cooling are shown. Simpler, no weight of the coolant, more resistant to battle damage. But the cons are large amounts of cooling fins must be machined into the cylinders, requires special cowlings and baffles to work properly, looser tolerances for thermal expansion reduces fuel economy, and shock cooling must be considered. This is where rapid cooling arises on descent from altitude. In this condition, less power is demanded of the engine because the throttle is back, so it's developing much less heat. In the descent, the airplane's airspeed increases, simultaneously increasing the cooling rate of the engine. As metals expand and contract under this temperature change, dimensional changes in the engine may exceed tolerance limits. Liquid cooling is similar to what cars do. A coolant is pumped through a radiator. Some of the pros and cons of liquid cooling are it's a low frontal area, less drag, and you can get tighter tolerances, which increases fuel economy and less danger to shock cooling. But the cons are there's additional weight and complexity of the cooling system and loss of coolant if you get battle damage. Inside of a cylinder, fuel and air are mixed, compressed, and then ignited. As this fuel-air mixture is ignited, its explosive force moves the piston inward. These pistons are connected to a crankshaft, and when the pistons move in and out, that causes the crankshaft to rotate. The propeller is connected to the crankshaft, so as the crankshaft rotates, so does the propeller. We've covered this so far. The cylinders undergo a continuous 4-stroke cycle. The 4 strokes are called intake, compression, power, and exhaust. The first stroke, the intake stroke, is when the piston inside the cylinder moves away from the cylinder head. As the piston moves away, the intake valve opens and the fuel-air mixture is sucked into the cylinder's combustion chamber. Once the piston has reached the base of the cylinder, it's time for the second stroke, compression. During this phase, the intake valve is closed and the piston reverses direction, moving back towards the cylinder head. This compresses the fuel-air mixture since it has nowhere to escape. Once the piston approaches the top of the cylinder, we begin the third stroke, the power stroke. Two spark plugs at the head of a cylinder each let off a spark which ignites the fuel mixture and makes it combust. This controlled explosion pushes the piston back inwards toward the base of the cylinder, which rotates the crankshaft and therefore the propeller. Finally, we've reached the last stroke, exhaust. During this phase, the exhaust valve opens and the piston moves back toward the cylinder head, pushing out the combusted gases, commonly called exhaust. Then the process starts all over again, repeating the process thousands of times every minute. On a typical four-cylinder engine, each one of the cylinders is in the middle of a different stroke. That way, one cylinder is always in the power stroke and the engine is able to keep the crankshaft rotating, thereby allowing the remaining cylinders to go through their respective strokes. As we saw in these four strokes, there are two valves at the head of each cylinder that is open and closed to allow the fuel mixture in and the exhaust gases out. But what controls those valves? The answer is the camshaft. A camshaft is a rotating cylinder situated above the crankshaft with various oblong lobes protruding from it. These lobes push on rods that connect to each valve, pushing them open. The valves are spring-loaded and will return to the closed position as the camshaft lobes move away from their respective rod. Getting the valves to open at the exact moment is very crucial for the engine to operate. Because of that, the camshaft is geared to the crankshaft so that they will remain synchronized. The camshaft is geared to spin half as fast as the crankshaft. This results in the valves opening twice during the four-stroke cycle. Now, how do we get the fuel and air into the cylinders? Well, that's the induction system. Inside the cockpit of most general aviation aircraft, there are throttle and mixture controls. The throttle controls the amount of fuel and air that go into the cylinders, while the mixture controls how much fuel is mixed with the air. In simple terms, the mixture controls the ratio between fuel and air. Typically, for every fuel molecule, there are 15 air molecules. The mixture adjusts the amount of fuel necessary to maintain this ratio. The throttle, on the other hand, controls how much of that ratio is let into the cylinders. The more the throttle is open, the more fuel and air enters the cylinders, and therefore the more power the combustion will be, making the engine run faster. The air as part of the fuel-air mixture comes through an air filter, usually found in the front of the airplane. Once the air passes through the filter, it is metered and sent on its way to the cylinders. The fuel, on the other hand, is housed on board the airplane, typically inside the wings. And just as air is metered and then sent to the cylinders, the carburetors and fuel injectors control the fuel-air mixture. The ideal horsepower generated in the four-stroke cycle is the green hatched area on the plot of pressure versus volume. Real or actual power is affected by things like friction, exhaust back pressure, induction losses, accessories, and cooling. So the actual horsepower generated will be less than the ideal horsepower. Next, we'll discuss altitude and turbocharging effects. As altitude increases in a normally aspirated engine, it reduces exhaust back pressure. Thus, you actually get an increase in power. However, it decreases inlet pressure, which reduces power. And this combined effect results in a net loss of power as you go up in altitude. Turbocharging increases back pressure, thus it reduces power. However, the compressor greatly increases inlet pressure, which increases power. The combined effect results in a significant increase in power. The altitude at which the wastegate fully closes in a turbocharger and that the engine still produces full power is called the critical altitude. When the aircraft climbs above the critical altitude, engine power output decreases as altitude increases, just as it would in a naturally aspirated engine. For reciprocating engines, the output torque is a function of combustion gas pressure. The mean effective gas pressure during the power stroke is called brake mean effective pressure, or BMEP. Using BMEP, the brake horsepower can be expressed using the equation shown, where D is the engine displacement and N is the RPM. This equation shows reciprocating engines can almost be considered an air pump with the pump capacity affecting power output. The pressure and temperature of the fuel-air mixture determine the density of the mixture entering the cylinder. As a result, manifold pressure is used as an indication of engine power along with RPM and inlet air temperature on most power charts. Engine power charts have two sides. The left-hand side, or sea level side, is where RPM lines converge upon friction horsepower. This side is determined from a sea level engine calibration. The right-hand side, or the altitude side, has the RPM lines developed from the equation brake horsepower at altitude equals brake horsepower at sea level times the density ratio minus 1 minus the density ratio over 7.55. A non-standard temperature correction can be applied using the equation shown. If temperature is in Celsius, you would add 273 instead of 460 to the standard and test date temperatures. A turbocharge correction can be applied using the equation shown. A 1% increase in brake horsepower for each 2 inches of mercury decrease in back pressure. Manifold pressure must be corrected to standard conditions using the equation shown. The only way to get familiar with an engine chart is to run through an example. This will tell us the performance of the engine at a given flight condition. For this example, we'll use the Continental IO360 at the following conditions: 2600 RPM, 24.3 inches of mercury of manifold pressure, 60 degrees Fahrenheit for outside air temperature, and 2,500 feet pressure altitude. An engine chart will typically have a step-by-step set of instructions in the upper left or upper right-hand corner. So we'll go through these one by one. Step 1, which is highlighted in yellow, says to locate RPM and manifold pressure on the altitude chart, which is the right-hand chart. And we're going to give that point A. For our example, manifold pressure is 24.3 inches of mercury, and the RPM was 2600. You can see on the right-hand chart that I've put the 24 and 25 inches of manifold pressure in red, and so you can see where 24.3 would be. And I've also put the 2600 RPM line in red. So you find where the RPM and manifold pressure intersect and mark that point on the right chart with the letter A. Next is step 2. Locate our RPM and manifold pressure on the sea level chart, which is the left chart, and label that point B. Again, we're looking for 2600 RPM and 24.3 manifold pressure. We see that manifold pressure is on the x-axis, and I've put 24 and 25 in red to show you where 24.3 would be. And then we just have to find the grid line that corresponds to 2600 RPM, and I've put that in red as well. So where those intersect is going to be our point B. Step 3 is to transfer HP of B to the altitude chart C. What this means is just take your point B and draw a horizontal line until you intersect the y-axis of the right-hand chart. And then you'll label that point C. Step 4 now says to draw an operating line that connects C to point A. So I've drawn a line from point C to A, and you can actually continue that straight line beyond A. Step 5 is now to locate our pressure altitude, which is 2,500 feet, on the operating line and then label that D. So we go to the very bottom of the right-hand chart where we see pressure altitude as the x-axis, and we find where 2,500 feet would be, and then we extend that up vertically to where it intersects the line we just drew from C to A. And where that intersection occurs, we put another point and label that point D. For step 6, we start at point D and we go horizontal until we intercept the y-axis on the left-hand chart, and we read off the standard day brake horsepower. For this example, it's 164.4. The last step then is to get the brake horsepower of our test day. To do this, we use the brake horsepower of the standard day we just found, 164.4, and then we have to use the equation where we plug in the standard temperature for 2,500 feet altitude and then what we recorded for our test temperature at 2,500 feet altitude. To figure out what the standard temperature is, we can use the graph at the lower right where we start at 2,500, we intersect the standard line, and then we read off the temperature. You can see it basically looks like 50 degrees would be the standard temperature at 2,500 feet on a standard day. So we'll put that in for TS. And then for our test day temperature, we used 60 degrees is what we recorded in the air at 2,500 feet, so we'll put that in the equation and run the numbers, and you'll find that the brake horsepower for the test was at 162.8 horsepower. In summary, we dissected a reciprocating engine. We examined the 4-stroke cycle of intake, compression, power, and exhaust, and we discussed methods of aspiration, fuel-air mixing, ignition, and cooling. We also discussed types of propellers. Basically, there's fixed pitch or there's constant speed. And then we just finished walking through an engine chart example. This concludes the module for reciprocating engines.